Hello, welcome to the talk. We're here from Okta. If you're not a user administrator, you might know us as basically a single sign-on company. We have a lot more going on in the back for overall identity management. My name is Jason Erickson. I've been at Okta for about 8 years. This picture is probably about a little older than that. I spent the last 4 years focused on developer productivity for our largest code base. We call it the monolith. It's not an original name, but that's what we call it at Okta. And it's the main Okta service application.
Hey folks, I'm Anugrah Singhal. That's the correct pronunciation. I've been at Okta for the last 2 years. I've been working with Jason on the same developer productivity team. Jason won't say it, but I think he calls me his most irritating hire yet. So what are we going to talk about today? This will help you decide, are you in the right talk or are you here just to digest lunch? First, we'll talk about the problem solving cycle, observation, hypothesis, experiment, and observe again. We'll drill in on the observability build, and then we'll go through some examples of the problems we had to solve. And finally, at the end, we should have some time about some Q&A. And as a disclaimer, this is not really a tips and tricks kind of talk. It's more about an approach to solving these problems. So yeah, so when our team started in 2021, we heard developers complaining about builds taking around 25 minutes. What does that feel like? I don't know. I'll just grab a quick coffee while I wait for this process. It was our #1 developer complaint. And we know that context switching kills productivity and takes you out from the flow state.
So we have a lot of specific examples that may or may not apply to your particular situation. Any large code base more than a few years old is bound to have its own peculiarities. So what we're going to talk about that is actually relevant to your situation is this cycle. Observation, form a hypothesis, make a change, measure again. It starts and ends with observable measurement. Do you actually know how long it takes? Do you have empirical data from people's experience or just what's going on in CI? How detailed are your measurements? When you make a change, how do you know whether things improved or not? As we go through the examples, I think you'll see this pattern emerge and maybe start to think about the same loop and how you can apply it to whatever's peculiar about your code base. So you can't fix what you can't measure. So who here has a pretty good handle on local developer build times? Raise your hand. Okay, so several, but not most, which is interesting, and frankly, it's not surprising to me. So you probably don't have a lab to run controlled experiments. And also controlled experiments are interesting, but sometimes you really want empirical data. So very clean data may be hard to come by. So borrowing some format from the Agile Manifesto, I'll talk in terms of valuing one aspect over the other. Things on the right are valuable, but not as valuable as things on the left. So specific over general. A good metric is well-defined and unambiguous. So like instead of build time, you would say median time to execute Maven clean install, for example. So it's like, what are we actually really talking about? Relevant over easy to measure. So measuring something just because it is easy to measure is a common pitfall. You could just like look up the flops benchmarks of the models of the laptops you have, which is interesting, but like it's not like what are people actually experiencing. Simple and explainable over complex and opaque. The most effective measurements are often the simplest, and they should be easy to understand and communicate. Consistent over intermittent. So if you ask a struggling developer to share their latest build time, it's better than nothing, but it's not as good as collecting all the build times on every build. And comparable over spot measurements. So a good metric allows for comparison over time or between different groups. So you can do like A/B testing, or it's really important for testing your hypotheses to be able to compare two different groups. So just to give a sense for the scale that we're dealing with, our code base is quite large, but it's not record breaking. So what do we mean by a large code base? When we started our team, we had about 4.5 million lines of code. And when the team, that was in 2021, and we add about 57,000 new lines every month. So we wind up with about 7.5 million lines today. Again, this is all code for one, or like our main service. So we have other code bases, but this is for the monolith. And build time is really a proxy for things that really matter, but that might be harder to quantify, like waiting, which is a form of waste, but build times are just one aspect of that. Developer frustration, other things. We said that a measurement should be specific. So what precisely are we talking about when we say build time? We mean time to do a full Maven build using developer profile. This includes execution plan, dependency resolution, compilation, special goals that we have for like UI building, protobuf generation, etc., package and install. It does not include running tests or static code analysis. So let's talk about the hypothesis. The hypothesis is our proposed explanation for what we're observing. A good hypothesis is specific. It points to a single concrete variable. Plausible. It's a logical and reasonable explanation for the observation. And very important that it should be testable. We can verify this hypothesis. You need to be able to verify the hypothesis by designing a targeted change and measuring again. So let's talk about the change or the experiment. This is where we test our hypothesis. So the goal is to make a targeted, controlled change to see if it produces the results that we predicted. So a good change is targeted, directly test the variable for our hypothesis. It's controlled, so we change only one thing and not 5, so we can isolate the impact. And it's documented, so we know exactly when the change was made and what it was. So that's an overview of the approach, but let's talk about what we actually did. As they say, it's not about the destination, it's about the journey. We are constantly looking for opportunities to improve, so we have lots of examples, but we want to share some highlights. In some cases, they gave us big performance improvements. In others, we simply had to work extra hard to hold the line while the size of the code continued to grow. So starting in 2021, we took our initial measurements so we could go from word of mouth to actually measuring what we were seeing, or measuring what people were experiencing. And then now that we're measuring, we could see the effects of some memory settings changes. We had work to do to properly leverage Apple Silicon when it came out. We did a Java upgrade that improved performance. And most recently, we tried out the Maven cache extension. So we'll start with one of the first things we did at the genesis of our team. So in 2020, there was a general understanding that it was getting pretty difficult for developers to work in our largest code base. So we started an initiative to try to address this, and that's when the monolith productivity team was created. We're a modest team. We're not, as he said earlier, we're not, meta, but it was a focused team on helping developers work in this code base. We had lots of things to improve, but for this talk, we're focusing on build times. And we were blind. So we had word of mouth for build times, but no way to know the baseline we were starting with, and no way to know if any changes we made would move the needle. So recall what goes into a good measurement. It should be specific, relevant, simple, consistent, and comparable. At the end of a build, we always get a pretty coarse measurement. It's actually pretty good at most of these, but the measurements are not recorded anywhere, so they're neither comparable nor observable. We tried Intuit's Maven Build Scanner. Maven Build Scanner is a tool that hooks into Maven builds and produces reports on the time Maven spent. This covered a lot of the same bases as before. And this would actually record the build times on every run. So it was an improvement. Unfortunately, it's still only local to the developer doing the build. And we needed to modify it to send the build data elsewhere. So we built a simple build data aggregator service and modified the build scanner code to send the data there instead of saving it to disk. From there, the build data aggregator would forward the data to whatever general observability platform you use or we use. At the time when we built it, it was Wavefront and later became Prometheus. And now we had all of our bases covered. We could actually start observing the build across all developers. It also had the advantage of being pretty easy to implement, self-hosted, and cheap.
So the first thing we're going to cover is our struggles with memory. So we know that build times have been getting longer and longer as our code base grows, and we receive occasional reports of out of memory errors. We're trapped inside this mode of getting people unstuck, but without the ability to look for the causes. We do not have enough resolution in our measurements to understand what is happening. So we understand we need a tool to give us more resolution into the data. We do a Gradle velocity pilot, and when we go into analyze the builds, we see that garbage collection is being thrashed on all of these machines with slower build times. And the reason was all of these machines had lower memory settings. Now that we saw that around 50% of our time of the 22-minute build was being spent in garbage collection, we had a good idea of what would fix the problem. We had already developed a facility to change memory options and push them to developers. So we decided to push a change. We decided to double the memory we were giving to the Maven build process. So did it help? Yeah, it helped by a lot. Our median build times were halved from 21 minutes to around 9 minutes. And it was incredibly effective to bring down build times for all of our developers.
So now we'll talk about our migration from Intel to ARM. So first, some context. So in June 2020, Apple announced plans to shift Macs to Apple Silicon, and then to enable x86 native software to run on the new ARM Macs, Apple embedded Rosetta in Big Sur. And then in October 2021, Apple announced the updated 14-inch and 16-inch MacBook Pro models with M1 chips and immediately discontinued Intel-based MacBook Pros. So our developers at the time were on a 5-year refresh cycle. So it takes quite a while for a substantial portion of the population to be on Apple Silicon. And also Rosetta seems to be doing its job. People with newer laptops are not reporting functional issues. Our, I would say, modest hypothesis was that building on newer, faster hardware should be faster, but how much faster? Anecdotal reports were that it didn't make much difference. We weren't instrumenting our data with the CPU architecture, so we added it. And what did we find? No builds. Nobody was building with ARM86, or ARM64. So this was a surprise, and we knew it wasn't actually true, so there was a problem with the instrumentation. So what's our hypothesis now? What if you were running Java through Rosetta? Would Java report x86 because x86 was being emulated? This is quite testable. So we wrote a tiny test program that prints out the value of OS Arch, and that would work. And then we could run it through Rosetta, and then we could get the ARM build of Java and run it, and we could see, yeah, that was the problem. So now we're back to our original revised hypothesis. Using native ARM64 Java will improve performance. So we changed our code that installs Java. So we had it scripted to push Java out to developers. And we saw that it was hard-coded to x86, actually. So we changed it to make it aware of the architecture running the code and install the correct Java native to your machine. And did it help? It helped a lot. So again, build time was halved. And so what was the result of this? Everyone got new laptops. Regardless of the refresh schedule, this might feel like cheating to throw money at the problem, but to get faster builds, but I prefer to think of it as having the data to justify the expense. So we were able to show the people with the purse strings the impact a new laptop would have for our engineers.
So we're gonna next talk about Java upgrade story. So even as developer productivity engineers, changes in organizations are often driven by things which are not really concerned about build performance. We were in the process of upgrading our Java code base to use Java 11, and to be honest, we were hopeful we would see performance gains as we are always promised with new Java upgrades. But our reality was that the builds got even slower and in the range of 10 to 12%. When we go into see our data, we see that we again don't have enough resolution in our metrics to form a hypothesis. So we need a better tool to get some deeper measurement. This time we decide to profile the build to see what's actually going on. What we see is that Java 11 is doing a lot more garbage collection cycles, much more than Java 8. And so let's talk about how the compilation works for a bit. So Maven has a build process with all of its plugins. Maven compiler is responsible out of the module compilation. And how we thought it would work is the Maven compiler would call the Java toolchain in an isolated process where Java C calls the Java C file manager to build the Java artifact containers for the jar files in the class path. And this is done for each Maven module for all of the 1400 modules we mentioned earlier. But how it actually works is it's not an all the Java C calls are not isolated. The Maven build process is a Java process, and when the Maven compiler calls the Java toolchain, it is in the same process as the Maven build process. So in Java 8, the artifact containers were being built and not discarded, but in Java 11, they were discarded per Java C invocation. So for 1400 modules, that's a lot of garbage collection and a lot of wasted IO when we know those artifacts we are building will be relevant later in the build too. So uh, the hypothesis was we could reuse these containers, and because they were needed again in the build too, but patching the Java compiler sounds intimidating. We really don't want to maintain a whole fork of Java, right? So now again some trivia. So Java 9 added an option called the patch module option. It's very helpful. It lets you perform surgical strike on a single module, replacing specific classes at runtime. This helped us avoid the overhead of maintaining a whole fork of the JDK. So coming back to the patch, we decided to add a caching layer to the Java compiler file manager where the contents of the artifact containers are stored throughout the duration of the build. This reduces garbage collection cycles and IO processes during the build process. And we measure again. What we see that we see a 15% savings over even over the Java 8 build. So yeah, and so what's next? Build times have been flat for quite some time, but we are always looking for ways to improve developer velocity. And as the saying goes, the fastest work is in the work that you don't do. We decided to experiment with caching. The hypothesis here is that when most developers make a change, it would affect only a small subset of modules, and therefore caching should help. So we decide for this change, we only wanted to target a small set of users. We wanted to tag every build that was cache enabled, and then have them be observable against non-cache builds. This aligned with the measurement requirements we talked about earlier. This was specific, relevant, simple, consistent, and most importantly, comparable. I'll be honest, when I added the cache extension, I did not expect perfect cache hits on the first try, but I also did not expect it to be so bad. We got only 4 cache hits on the first try, but with a code base as big and diverse as ours, with various non-Java files, out of band Maven exec scripts, I would say it's not that easy. So what we hope would be a straightforward process, it turned out into a more iterative process where we did a bunch of refactoring to our build to get to 100% cache hits. We started by including all of the non-Java files and folders. Then we got rid of all of the out-of-band Maven scripts and excluded some of the Maven goals which produce timestamp files. We also had to do multiple dependency graph changes to reduce all of the Maven dependency anti-patterns that had built over the last few years. And we did get 100% cache hit with those, but it was still not enough. The last and important part was with all of these changes, it did not work with the IDE. So we solved that by attaching build outputs to the cache extension, which it does not do by default. We had to let go of some performance for it, but well, I think working with ID is actually a requirement. So where do we get to finally? So some of our users have a median build time of 2.5 minutes now. Uh, it's not a universal story. Not all of our developers experience the same bliss, but as you've heard in the previous presentations, 2.5 minutes can still take you out of flow state. So you're never finished improving developer experience.
Yeah. So we covered a lot of our journey today, from team inception to today. We talked about our observation hypothesis change loop. We talked about several examples of putting it into practice, and it works. But of course, as my colleague says, you're never finished. There's always more to do. So the number one thing I would say is that if you're not measuring in a way you can observe, find a way to start doing that. And there might even be some companies here that can help you with that kind of thing. I don't know. Yeah, so with that, I guess we can take some questions if there are any.